Good morning, everyone. Thank you for coming to Contemporary Issues today. We have a rather explosive topic today. Because it's about the pathway to the development of the atomic bomb. And so Ron is going to do a very interesting and speedy presentation today on how that came about, and topic or timely with the Oppenheimer movie. I'm sure, how many folks here have seen the Oppenheimer movie? A lot of us here, on the development of that and the moral dilemmas too, because you probably know in that movie Oppenheimer talked about, I have blood on my hands and we had to develop the bomb, but we also feel bad about it. And so pros and cons, it's a fascinating topic, I think. And so with that, before we get started, I want to welcome any first-time visitors. Glad you are here. I'm Steve, this is Ron, and we talk about social issues a lot from a Christian perspective. We try to do that, balance and show both sides. Our other announcements, Zoomers, please mute yourself on the lower left corner of your screen to keep our background noise down. And we are recording this for future playback on YouTube for those who can't be here, because we have a lot of things going on at the church today. And please put your phones on silent if they're not already, so we keep that noise down. I want to give a plug to another class that's going on today. Dr. Peter Van Arsdale was here. He has a class at 11:45 on critical race theory. You ever wondered what that is and how it's taught? How widely, I'm going to ask how widely it's taught across the country, or if it's not really a big issue. Maybe some parts of the society make more out of it than is really warranted. I'd like to know all those kinds of things. 11:45 right across the hall here for that. And another class, Celtic Spirituality, starts tomorrow with an ILIF scholar at 6:30 on next couple of Mondays. Should be a good class too. Okay, any other announcements? 3:00, big concert today, the Requiem. Ron is playing in the orchestra. 3:30 today. Thank you.
Doors open.
Should be. Doors open at 1. Well, if it's like the 9 o'clock service today, it's going to be crowded. We had so many, there was hardly a place to sit today. It was amazing. Yeah, that was good.
They want to come and give their money away.
That's right. It could be done. Okay, we want to leave plenty of time. I want to mention a couple quick things that were relevant to our issues that we talk about here today. One was last week we talked about the Hamas-Israel war, and we may revisit that because it's going to go on for a while. But just this morning on NPR, there was a great analysis of it and a little update on how they may get the hostages freed. Because it's so hard to go underground and try and rescue those hostages in those caves that they have. The Hamas has proposed an all-for-all hostage exchange, they reported today. And so, and Netanyahu, the Israeli prime minister, said, no, we won't be doing that. But that's for the moment. That could change. And that would be the 240 Israeli hostages for the 6,700 Palestinian hostages. And you may think that's not possible, but the last hostage exchange they did was one Israeli soldier for 1,000 Palestinian hostages. So that may be more in the news as that proposal goes back and forth. Interesting. The other one I wanted to mention to you was there's a great NPR show called Science Friday. Some of you probably listened to. Yesterday, they talked about nuclear bombs and nuclear winter. And the scholar that was on there was saying there are 9 countries that have atomic bombs currently out of the 200 countries in the world. And those are America and its allies, Israel, France, and England, and then Russia and its allies, China and North Korea, And then the other two are adversaries, India and Pakistan. And he was saying if India and Pakistan had a nuclear war, the scientists know it would put up so much smoke in the atmosphere, it would cause nuclear winter, meaning that it would block out the sun, even in America. And in Central America, above our farmland, the average temperature would be below freezing in the summer. And so it would cause famine. So it's an example of nuclear winter. Yeah. So if you want to hear more, go on Science Friday website and listen to that episode yesterday. It was fascinating. I just love that show. Yeah. So on that cherry note, yeah, I want to thank Ron for putting this together and the 5 or 10 books he's read on the topic. And we'd like to hear more about it. Thank you, Ron.
Okay, well, thank you, everybody, for coming this morning. Career-wise, when I graduated from college, instead of staying at Wright-Patterson Air Force Base working on aircraft engines, I took a job with Goodyear Atomic, worked 3 years at the gaseous diffusion plant, uranium separation facility in Southeast Ohio. And then I jumped to Oak Ridge, where I worked about 8 years on the high-speed gas centrifuge. So I had a very strong interest in nuclear power, uranium enrichment, things along that line. Certainly having lived in Oak Ridge, got quite a bit of perspective from that experience. Had I done this lesson 15 years ago, I would have missed a lot that I will present today. I'm going to go very fast, but there's actually been a lot of information that's been uncovered, discovered, and even confirmed in the last 10 years that has made us realize that both Japan and Germany were much closer to having bombs developed and ready than we thought. Perilously close. In fact, a book I read just a couple weeks ago, Critical Mass, which I recommend to everyone to look at, is kind of I call it a Paul Harvey's The Rest of the Story to go along with the Oppenheimer book. Of course, the classic Pulitzer Prize winning book on the nuclear development and the making of the atomic bomb is this book by Richard Rhodes. This is the 25th anniversary edition of it. I read it when it first came out. I reread it here in the last couple months.
That whole thing you read?
Yeah.
Wow.
But also looking at some other materials, again, I recommend Critical Mass. This is literally a knock you out of your chair book. And Japan's Secret War, talking about where Japan was in terms of their bomb development. There's also been some pretty good books come out. Schiffer Publications, The Neutron's Long Shadow. This book's been out for about 5 years, but has quite a few pictures of both the Oak Ridge programs and the Hanford programs. Finally, I'm going to pass around a little card. This is not radioactive, but it shows you how much one fuel pellet can provide in terms of energy relative to other forms of energy. Also, at the end of class, I've got here a portable nuclear detection meter. These run around $500 or $600, but it will read alpha, beta, and gamma. And just to show you that you're constantly being bombarded with radioactive materials, I told Steve Bush before I just showed him this morning, I said, in this room, we're probably going to see a radiation count of 20 to 25 counts per minute. And I turned it on.
And sure enough.
And you'll see it march up to that. Also, at the end of class, if you want to look at a couple pieces of mineral that have a slight radioactivity, here's one from Floyd Hill, right here in Colorado, gadolinium. It's got an isotope of cerium in it that's slightly radioactive. So we'll get a count on this of about 150 counts per minute. And then a piece of dinosaur bone that has some uranium in it, and it will give you a count of 50 or 60 counts per minute. So if you want to look at those after class, you're most welcome to.
And those are safe, just don't sleep with them.
And then if you want to watch a movie, you don't know if you want to cry, laugh, or run in fear, watch the famous Dr. Strangelove, starring Peter Sellers and George C. Scott. So we'll pass some of that stuff around. Go ahead and pass some of these things around. And this is again the Bible of the bomb development. So we're going to move real fast. Let's get the slides up. Okay.
Thanks. Yeah, go ahead.
First slide shows a thermonuclear explosion cloud out in the Pacific, a very powerful one, and the mushroom cloud from that. That explosion was many, many times more powerful than Hiroshima. Next one. Again, a couple of the resource materials. There's a good biography that's just come out on Leo Szilard. He appeared in at least one of the Oppenheimer movies. It's the guy in the bathtub. Okay. Next one. And again, I recommend these two books that have really come out and given us a lot of information of additional facts that have come out in the last decade or two. Critical Mass and Japan's Secret War. Next slide. We're going to start off with the discovery of the atom. Early 1800s, chemist John Dalton discovered a pattern known as law of multiple proportions. He found that when the chemical elements came together, they tended to combine in distinct ratios of the elements. And he called this basic unit of weight an atom. By the way, that picture in the upper right corner of this slide shows the highest resolution image of atoms ever taken. Cornell University folks captured this picture in the last 5 years. It's in the Guinness Book of World Records. Next slide. Discovery of the electron. 1897. Thomson discovered the cathode rays are not electromagnetic waves, but particles deflected by electrical and magnetic fields. And he found these particles were 1,800 times lighter than hydrogen, a hydrogen atom. He discovered the electron. There's also a picture in here of electron clouds. Unlike the planets in our solar systems, where you can predict where Jupiter is going to be next year in its orbit, you can predict where Mars is going to be, you can predict things coming into our solar system like comets and get a pretty good idea of where they will be. But electrons have what we call electron clouds. Those are pictures that represent the probability density of where an electron might be. It's whizzing around, but it's not following a circular or elliptical orbit. All you can say is there's a certain probability that it will lie within certain parts of those clouds at certain times. But you can't accurately say where it will be at the next microsecond. So again, those are electron clouds and very informative. So we've figured out the electron, and then in 1927, and that's really pretty late in the scientific time, Chadwick announced the possible existence of something called a neutron. So we didn't even know about a neutron until 1927. And of course, since then, we know now with modern technology, neutrons are not the smallest particle, but they consist of smaller particles called quarks. A neutron is one up quark and two down quarks. Proton is two up quarks and one down quark. But enough of that, and that's a whole nother subject. Next slide. A mass spectrometer. A mass spectrometer was invented, and they found out if you put an ion beam through a magnetic field, it would deflect particles. And it deflects the lighter guys more. The big fat boys don't get deflected as much by the electron field. And you can use this principle to determine what is in that ion beam. And you can watch the different ions go to different slots of degrees of deflection and figure out what's in that ion beam. And this principle can also be used not only to analyze things with a quote mass spectrometer, but also to separate the ions. If you know where to put the window and how strong to make the magnetic field, you can get the substance you want to go down that slot and separate it. And several isotope separation techniques do use the mass spectrograph principle to separate isotopes. Next slide. H.G. Wells, World Set Free novel, written in 1913. H.G. Wells was quite the visionary. In fact, his book may have influenced the development of nuclear weapons. Leo Szilard, physicist, read the book in 1932, and the year the neutron was discovered in 1933, Szilard conceived the idea of a neutron chain reaction and filed patents for it. But again, the World Set Free, that novel really opened up a lot of people's eyes to the fact that there might be a power right in front of us every day that we didn't realize.
Did he talk specifically about breaking the atom?
He talked about what he foresaw the coming of, it says aircraft, tanks, a sexual revolution, the atomic bomb, War of the Worlds. Yeah,
Wow.
quite the visionary. Next one. So, we also want to mention Leo Szilard, and this book is fairly recent on Szilard, and he didn't get the fame of Einstein, Fermi, or Oppenheimer, or Teller, but he was really a father of the atomic bomb and the atomic scientist. By the way, he was born in Hungary, educated in Berlin, and escaped Germany in 1933, where he first developed the concept of a nuclear chain reaction. Next slide. Szilard had patents on a lot of advanced concepts. He conceived the nuclear chain reaction in 33, patented the idea in 36, and he helped get together and draft a letter that Einstein wrote that was delivered to Franklin Roosevelt. Szilard and Fermi got together with Einstein. They had Einstein draft a letter to President Franklin Roosevelt and warned Roosevelt that nuclear bombs and nuclear technology could be critically important for us to win the war and even to survive as a civilization. Fortunately, we had a smart cookie that was open to thinking in the presidency at that time. FDR embraced, understood, and took action to set the motions in action for the Manhattan Project. But we have to give a lot of credit to Szilard, who did not get the credit he deserved. He also had some great inventions in terms of medical technology, in terms of vaccines and other things. Next slide. Germany, we can say if the race for the atomic bomb was a football game, definitely had the lead at halftime. 1938, the German chemist Otto Hahn directed neutrons into uranium atoms, expecting to get transuranium elements, but he ended up getting products from that neutron bombardment of uranium that he had not expected. And Hahn's result was the first experimental nuclear fission. Next slide. So Germany actually had the first fission. There was also a couple people under the auspices of Hahn who kind of didn't get the credit, like a lot of women. Lisa Meitner, a German Jewish woman, is sometimes called the mother of the atomic bomb. She never won a prize, but she worked with another gentleman, and they ended up affirming that the fission experiment had literally split the atom into distinct particles that went elsewhere on the periodic table. Next slide. Of course, Hitler and his anti-Jewish venom played a key role in the German effort toward an atomic bomb. We all know, what does this say? The first anti-Jewish law Adolf Hitler promulgated was in April 1933. We stripped non-Aryan people of many high-position jobs in government and universities in Germany. So Hitler really got kicked in on his anti-Jewish, anti-Aryan, non-Aryan folk theme in 1933. And of course, it got worse as he went along. And he started persecuting Jewish people and Jewish scientists, particularly. Next slide. There's a timetable of the German descent into fascist dictatorships. 17 million fell victim to the Nazi regime. And Kristallnacht, Night of the Broken Glass, happened in, what year was that? 1938, yeah. Or even a little bit, or was it 36? At any rate, his hostile attitude toward particularly Jewish scientists played a key role in driving hundreds of Jewish scientists and engineers out of Germany, dispersing many of them to the United States and to England. Next slide. Okay, Niels Bohr. You've probably heard of his name, and perhaps a chemistry class. A Danish-born gentleman. His mother was a daughter of a prominent Jewish banker. So he had a mom that was Jewish, but he wasn't a practicing Jew or didn't consider himself mostly Jewish. Nonetheless, he got out of Germany, got out of Denmark, came to the United States, and did what he could to try to help a lot of Jewish scientists that were being persecuted to try to get out of Germany in the 30s. And many, many of them did successfully do that.
He was in the Manhattan Project. Right?
Yes.
Yeah.
Next one. So after Niels Bohr, you probably also heard of Enrico Fermi. Fermi was a brilliant Italian physicist, way ahead of time. He demonstrated that nuclear transformation occurs in almost every element subjected to neutron bombardment. So if you want to split an atom, the way to do it is to fire a neutron at the nucleus of an atom. And virtually every element on the periodic table will react to some degree to a neutron bombardment. Some very little, certainly uranium and plutonium, a great deal.
And that's the basic idea of the nuclear bomb or atomic bomb, breaking the atom apart and the energy inside blows up.
Yeah.
Okay.
The energy in one atom is distributed to the products, but there's a lot of leftover, and that leftover energy can be harnessed. Okay. Fermi exits Italy. The war against Jews spread to Italy and threatened Laura Fermi, Jewish wife of Enrico Fermi. So from what I understand, Fermi was not Jewish, but his wife was. They were persecuting his wife, in essence, persecuting him, his family. So he got the heck out of Germany. He went up to accept the Nobel Prize in 1938 up in the Netherlands or what was Sweden, wherever they hand out the Nobel Prize. And he took the last train to Clarksville to head for the United States instead of returning to Italy. Yeah, it said he went from Stockholm to New York. He did not return. So there's another brilliant mind that was picked up by the American scientific effort as a result of Jewish persecution. Next slide. Some factors that slowed the German lead for the atomic bomb. Again, they made the decision to expunge the country of a tremendous amount of scientific talent because they were simply Jewish. And there was undoubtedly, unquestionably, an incredible amount of Jewish scientific talent in Europe. We can talk about why, but it's simply a fact. There were tremendous amounts of intellectual knowledge in many of the Jewish people at that time. Bigotry against Jewish scientists had thoughts about the doubt of the atomic weapon. Hitler was prejudiced. Also, as the war went on, Germany did look at how much effort they were putting into the bomb development. They had struggles finding enough assets to put into their bomb program. Also, nuclear weapon for a while there in Germany looked like it was too far ahead to impact the war effort. So they spent a lot of time putting money into the V2 rocket, the gas turbine jet engine, and other technologies. Also, the Eastern Front, as the war with Russia turned sour, they were forced to put more and more resources into trying to stop the Russian counterpunch to their invasion of Russia. Next slide. Japanese effort for a bomb. The book, and I won't, in a nutshell, they found that the Japanese did have some efforts going on, and they had a pretty major effort going on in North Korea near the Chosin Reservoir, drawing electrical power from the Chosin dams to power some electromagnetic separation methods. In fact, the next slide shows a picture, next slide, taken by the US Marines when they went north of the 38th parallel during the Korean War. That's a picture of a major Japanese complex in North Korea. And as the analysts studied the shapes of those buildings, and the photo analysts looked at it, they discovered that one of the buildings looks incredibly similar to the United States S-50 Oak Ridge thermal diffusion plant. And there's strong evidence in that picture of several of the constituent industrial components you need for a major uranium enrichment effort. The book even conjectured that maybe the Japanese test fired a small bomb in the ocean off Korea. It was not, they don't think if it did happen, and they're not sure, it did not have the yield nor the efficiency, and their electromagnetic separation technique was not advanced enough to give them tremendous amounts of uranium, but they were on their way. We couldn't just pretend that there was no chance of Japan getting a bomb. Next slide. Again, the method that the Japanese were using, it looks like they were trying to use liquid thermal diffusion. And again, there was a plant in Oak Ridge. There's a picture to the left and to the right of some of those liquid thermal diffusion uranium enrichment facilities in Oak Ridge that are shown in the larger book that I'm passing around. Some good pictures of them. Okay, next slide. Again, fission in 235. For those of you that love rock songs, remember the song Feeling Groovy? Slow down, you move too fast. You got to make the morning last. Anybody remember that one?
Sure.
Well, this is one of the scientific principles they found out you needed with neutrons. If you just knock an atom apart, you get fast neutrons coming out. I mean, they're moving almost light speed, like literally like bats out of hell going out of there. And to get them to get a chain reaction going, it's like a billiard ball striking one and moving balls around the pool table, you need to slow them down. Slow down, you move too fast. How do you slow them down? You put in a moderator. So now, what's a moderator? It generally is a light element. One of the best ones is heavy water. Normal water does pretty good, except it also absorbs a lot of those neutrons, keeps them from going along on the pool table to the next target. But heavy water is beautiful in that it will slow the neutron down, but not absorb it. Send it along to potentially keep a chain reaction going. And that's what you want. You want a chain reaction for a nuclear power plant to keep the reaction going. And you certainly want a chain reaction for a bomb. Next slide. Okay, we'll go over this one real fast, but this shows us. You say, what the heck is this complex thing? This is the probability of plutonium and uranium, specific isotopes, absorbing or continuing a chain reaction. And it turns out that plutonium and uranium are by far the best elements and isotopes to keep for fission and to keep a chain reaction going. There are a few other elements that will do it, but by far, and this also shows the x-axis is the speed of the neutron. And they found if you move to the left side of the x-axis, those are the slower moving neutrons. You see that the absorption, not the absorption, but the fission cross-section, as they call it, the plutonium and uranium goes way up. Notice that y-axis scale is not linear. It's a logarithmic scale. So a slow neutron has many orders of magnitude higher probability of fission than the fast ones. Okay, next one. All right, so there's the fission of U-35, and again, you want the chain reaction. When a uranium-235, there's different isotopes of uranium, undergoes fission, for every U-235 atom you smash, you release 2 or 3 neutrons. And if you keep those going and have them strike another and another pool ball, you got yourself a chain reaction. Again, you want a moderator, and heavy water is one of the best. Helium is also another good moderator, and water will moderate, but it'll also absorb. So you kind of don't want water.
Quick question, Ron.
Fire away.
So in the movie also, they were worried that when the first bomb went off, that it was going to continue with the chain reaction into the air and destroy the world. What made the chain reaction stop just in that bomb that they did and not continue on in the air? Was it the heavy water moderator?
It's largely the fact that the other constituents of the air, just nitrogen and oxygen, can't be fissioned very well.
Okay.
Can't simply, they're not.
They had to
Yeah,
keep
You
it
gotta
in
get
that compressed bomb space.
you need a critical mass of the right stuff,
Yeah,
and it's got to be concentrated and sustained concentrated.
and it couldn't in the air.
It won't just head across this room.
And thank God it wasn't.
Yeah.
Sue.
What is heavy water?
There are 3 basic isotopes of hydrogen. Hydrogen, of course, is one of the 2 constituent elements of water. Normal hydrogen is just a single proton and an electron. Heavy water, or deuterium, is a proton, an electron, just like regular water, only throw in a neutron. It's got a neutron in there as well. And then there's also tritium, which has 2 neutrons. So the different isotopes of hydrogen differ by just, do they have 0, 1, or 2 neutrons? And for nuclear power and for moderation, you want the neutron guys that have 1 or 2. Good question. Next one. Okay, there was some movies and TV programs but there was a heavy water plant in Norway that the Germans were protecting and using to send heavy water back to Germany. And there was a daring commando raid, a couple of them, to blow up that plant and also destroy a ferry boat that was conveying some of the heavy water across a fjord in Norway. Exciting story. Next slide. Now here comes the knock you out of your chair part of the story today. From the book Critical Mass, and this is not fiction, this is true, it's been affirmed. Just days after the fall of Germany, a large submarine, double or triple the size of normal U-boat, packed with barrels of uranium. Also, had on that crew were 2 Japanese scientists. And quite a few documents. They explain how to build the V2 rocket, the V4 rocket, aircraft engines, some other advanced technologies, and there could have been some atomic bomb data, how to build the bomb. The intent was to send this U-boat to Japan, to give all this knowledge to Japan, and perhaps allow Japan to incorporate this technology and continue the war. As recent as 2007 or 8, they didn't think that the uranium on this boat was enriched, but they've now discovered that absolutely it was enriched, and it was, fortunately, the captain of this boat sort of semi-defied orders and decided he was going to give this carload of uranium and secret information and deliver it to the United States, not to give it to Japan. And the 2 Japanese guys on the boats committed hara-kiri. And there wasn't a unanimity of opinion even among the Germans on the boat to give it to the United States. But we ought to give the guy that was the captain, the German captain of this boat, an award, because he made sure, took careful steps to get the boat into the hands of the United States. They also in 2011 found in Germany near Hanover a major cache of depleted uranium. So the combination of the finding of that cache of uranium, depleted uranium, and then this cache of enriched uranium, a large quantity of it, that was fed into the Manhattan Project, and they affirmed it by looking at the records from Hanford and Oak Ridge, that this carload of German enriched uranium enabled us to get enough uranium in time to make our first bomb to drop on Hiroshima. Also in this, as we worked on the fusion bomb, the bomb was dropped on Nagasaki. One of the big problems we had was getting all the uranium compressed into a ball in the center, and also compressing the plutonium. There wasn't plutonium in that bomb, but trying to get all the lens triggers on the outside to go off at the same time within something like 150 thousandths of a second of each other, to make sure the compression wave pushed it all together and got the bomb. Turns out, just 3 months before the Nagasaki bomb, we had not yet perfected the compression to get it, get the lens and get the simultaneous firing we needed to compress and get the bomb to work. On this sub, it looks like there was the German technology for not infrared, but ultraviolet initiators. And they took those the technology from those ultraviolet initiators and incorporated it into the fusion bomb program. And so this was the second thing that came off this sub that enabled our bombs to be on time. Had we not gotten this uranium, the production at Oak Ridge was still coming along well enough that we would have had that first little boy bomb about 3 months later than what we did. But it's definitely accelerated it by several months. And it's an open question for engineers. Without that ultraviolet initiator, how long would it have taken us to figure out a way to get the implosion technique working?
That was in the Oppenheimer movie. They talked about the initiator, and then they have to have the compression wave just right to then have enough power to break apart the atoms.
Mhm.
Yeah, so Oppenheimer was taking his team through that.
So I can't, again, this is a knock you out of your chair book. I'll go ahead and pass that around. I'd like to give an award to that German captain.
Yeah, what happened to him?
I will have to do more research, but there's more to the story. There's the rest of the story is, we would say, of were they trying to get Martin Bormann, Hitler's #2 man? Was he on that sub, or were they trying to get him out of the country? Oh, and that's a mystery that we're not sure of. Okay,
Ron,
again, go ahead.
do you happen to know what happened to all the people on the sub? And did the sub landed in the United States?
Oh, yeah.
Did it?
It
What happened to
surrendered.
the people?
The captain made every effort to get into the United States sector of the Atlantic Ocean and to surrender to a US destroyer, the USS Sutton, who escorted that. He didn't want to surrender to the Canadians, didn't want to surrender to the British French sector. He got into the United States sector zone of the Atlantic Ocean, surrendered to the USS Sutton, who took the boat, escorted it to Portsmouth, New Hampshire. And that material was quickly taken off the boat and gotten into the hands of personnel in the Manhattan Project. Fascinating story.
What happened with the people?
The two Japanese guys committed harikari, and I'd have to follow the tracks of the other crewmen and the officer. Okay,
Good movie.
again,
Yeah.
back one. What we got off the German boat, go back one more.
Click.
There we go. Okay, yeah, so there's the sub. There's a picture of the Oak Ridge electromagnetic separation. The middle picture is a German scientist who apparently came up with an electromagnetic separation technique that was maybe 4 times superior to what we had. And that was probably the basis of their very successful uranium enrichment program, which 15 years ago, we didn't know this. This information has come out in the last couple decades. Next slide. What we got off the German sub, about 80 drums of 15.5 pounds each of very enriched uranium. And then in 2011, of course, they discovered that 126,000 barrels spent uranium in Germany. That was further affirmation. They had the enriched uranium, they had the depleted uranium, massive quantities of both. Conclusion, they knew how to enrich uranium, and not just minuscule amounts. Strong evidence Germany had a very productive uranium enrichment plant, and they believe there's strong evidence it was near the Auschwitz concentration camp in Poland. And if you read the book, it talks about why we think so, what evidence there is to back. So, and again, then of course, the U-234 also had the ultraviolet light warhead triggers, which were incorporated into our bombs. So a picture I drew here, the story told by Richard Rhodes in the Atomic Bomb book is a good one. It's not wrong, but it just failed to put in this major branch came into the effort that came from Germany on the U-234 side. So I think we would have gotten to all our goals without this. But this certainly helped us, got us there quicker, and we can conjecture what might have happened had the stuff not come to us and gotten in the hands of the Japanese or the Russians before us. Go ahead.
How is it that we are just learning about this now? What happened? Did we find some book or some evidence? I mean, this is several years later.
Yeah, the answer is declassification of some documents and there's some researchers that went into the National Archives with the Freedom of Information Act to look at the uranium delivery schedules. And they found that there was a huge spike just a week or so after the German sub landed. and deliveries to Los Alamos. So. And it was kind of kept under, there's political reasons. They didn't want to, yeah, political hot potato.
This triggers a question in my mind. When was the uranium mining so prevalent over on the western slope? People were moving there to get in that money, and what happened?
Answer, buy the book, which I've got 2 copies of, Uranium Frenzy. But it talks about how the Moab uranium rush was, I think, very early 50s, pretty much. And it was a tremendous surge. Try to find uranium and pay big prices for it. So, okay. Okay, I've talked a lot. Let's try to whip through these last couple slides. Again, get the book Critical Mass. The flight of the Enola Gay, there's the first bomb and the second bomb. The Enola Gay tail gunner, Bob Karen, lived here in the Denver area.
Oh,
There was, I clipped out 20 years ago when I saw his obituary in the Denver paper. He was the tail gunner for one of the flights. I think it was the second flight. Or wait, Enola Gay, yeah, that was the first one. Yeah, we'll pass a few more things around. Okay. All right, next slide. Again, you want fission or fusion? And here's a plot for those that are scientific oriented.
what's the difference, Ron?
Fission is splitting an atom into a couple constituent pieces and stealing off the excess energy. Fusion is the opposite, is pushing together and binding two atoms together and taking the excess energy off. And it all depends if you're a really light atom, less than iron in atomic weight, fusion is possible. Once you get above iron on the periodic table in terms of atomic weight, we get into the fission range. So it just depends on if you're above or below iron on the periodic table that you want to go with either fission or fusion.
When do you think we'll have fusion?
Cold fusion.
The answer is they're making progress. Latest guess of mine is they're thinking 2060, 2065, good, really solid commercial viability. Maybe a few experimental units putting a little bit of something here or there by 2040, but most likely 2060 and beyond. Okay, next one. Again, Edward Teller is considered the father of the H-bomb. And again, if you want to get another book, Richard Rhodes, Dark Sun, The Making of the H-bomb. Good book to read.
Does the H-bomb mean breaking apart hydrogen atoms?
It means fusing hydrogen atoms together.
Okay.
Yep. And
Is it much more powerful than atomic bomb?
yes, in fact, it uses more plutonium. And plutonium bomb is more amenable. It's in a way perhaps cheaper to build, more efficient than a uranium bomb. And we've got a friend of mine on the screen today who has worked at Rocky Flats and knows quite a bit about plutonium.
Oh, a zoomer?
Zoomer, Celia.
Celia, yes.
Okay, next one. After Teller. We'll wrap up by saying that lithium and beryllium are very important for bomb making. Lithium, lightest of all metals, is a main fuel of a thermonuclear bomb for triggers. And beryllium, when bombarded with alpha particles, releases about 30 neutrons for each alpha particle. So it's a good spark plug initiator, keep the reaction going. So those are two important elements in the making of a thermonuclear bomb. Next slide, we're almost done. Actually, if you go on Wikipedia and look at thermonuclear warheads, it talks about how you In fact, most of the thermonuclear bombs today are multi-stage. They have often start with some other reaction in lithium, and then proceed to do a fission, a small fission, and then get the fusion going. So they're combinatorial bombs that have both fission and fusion. Fusion being the big source of the devastation, but both important. And again, if you go on Wikipedia, it also shows here the key plutonium pit that was made at Rocky Flats. And this also shows the lenses where you try to focus the energy of these initial explosions to compress and push and hold everything together long enough for the Big Bang. So there's your Big Bang theory.
Oh, is that what happened? God's
So
atomic bomb.
lithium
They
being a key
explain why
component of
lithium batteries
bombs.
explode.
Yes.
Yeah, well stated.
Catch fire.
Catch fire.
Okay, so lithium
Discussion?
battery and bombs. The final slide, and let's get some questions going on.
Just saying.
I love the caption on this. This is a nuclear torpedo that the Navy was working. And the caption under the picture said, this torpedo had a probability of success of 2, the target and the person that fired it.
Both blowing.
They figured it, but yeah, it wouldn't go far enough or get it far enough away and take out both the sub that fired it and the target. How many have seen the Gregory Peck movie On the Beach?
It scared me
Okay.
to death.
What's that?
It scared me to death as a child.
Okay, and then if you wanna both laugh and cry and have fear, watch Doctor Strangelove. So I've yacked probably too much today. But it's a subject I'm intensely interested in because
Yeah.
where I spent 10 years of my career. And so I hope I haven't scared you, bored you, or all the above.
Discussion, questions. Ron, why don't more countries today have an atomic bomb?
There's still a tremendous cost barrier to get over.
Okay.
And the countries are not eager, those that do have the bomb are not eager to share the technology.
Okay.
In a way, it's pretty terrifying. What if a sustained nuclear reaction was as simple to do as something you could do in your high school chemistry lab?
Yeah.
We'd have destroyed the world by now.
Well, lithium batteries come close.
Yeah.
I have a comment.
This is a terrific presentation. I really enjoyed it. It was really well done.
I have a comment.
Grant,
Fire
hang
away.
on. Grant, hang on just a second. Somebody else is asking one, then we'll get to you.
Oh, that's okay.
It's okay. Go ahead, Peter.
Margaret von Braun, the daughter of Werner von Braun, who many of you remember, is a friend of mine.
Oh, wow.
And it's nice to talk to Margaret about her father, who was a V2 rocket scientist in Germany, and then became the lead Saturn rocket scientist for the Apollo program in the United States. It's very interesting to talk to Margaret about some of the things on the social and economic and political side from Germany to the US as those scientific minds evolved. And as her father, as she's told me, was simply a scientist. He wasn't a politician. Well, it applied to a lot of the other folks too, didn't it, Ron?
Yes.
Who were not necessarily politicians, but were concerned on the science side.
Right. In fact, there were several scientists in Germany who were really nervous about Hitler, and yeah, we're not anywhere near 100% behind him.
Yeah, Margaret tells me blessedly, her father was not in any way a fan of
Yeah,
Hitler.
I have read the book Von Braun, by the way.
Yeah.
And every engineer that's ever taken systems engineering, that book ought to be required reading. He was maybe the father of systems engineering.
His daughter Margaret works on humanitarian projects, including in the mining industry, to minimize negative mining impacts on indigenous communities.
Wow, fantastic.
Interesting. Okay, Grant, go ahead, and then we'll do Mary.
I
Grant, go-
heard about 3 months ago that they had broken through the problem of the fission reaction to be held in an electromagnetic force, electromagnetic field, so that because there's nothing that's going to be able to hold it. There's an
You're thinking fusion, right?
uh, uh, uh,
You said
Fission.
fission. I think
Yes.
you meant to say
I'm sorry,
fusion.
I meant fusion. Fusion. It has to be held by an electromagnetic field because nothing is. It would just melt everything. So I heard that they may have solved that problem of the electromagnetic field to hold the fusion materials so that it won't touch anything and yet will give off enough energy so that we can use it for electrical and so forth.
Yeah, they're finding also that laser fields are potentially able to hold it together long enough. The big thing with fusion, of course, is for those that have seen Back to the Future, fusion delivers a tremendous amount of power, but like the lightning bolt hitting the clock tower in Back to the Future, it delivers a tremendous. You got to spread it out. You don't want it in one lightning bolt splash. You want to get that power distributed over a period of time.
Amazing. Mary.
I was just wondering, how many of these bombs have we produced that are ready to go?
There's literature on the US nuclear inventory in terms of number of warheads and number of warheads that are both out there in the field dispersed, ready to use, and how many are in storage. And it's thousands.
Too many.
They said on the NPR show yesterday, there was 12,000 worldwide. Used to be many more than that, but we did reduction programs. 12,000 across the world, and the smaller countries have about 200 each.
Thank you.
Better ways of killing it.
I lived in western Nebraska where there were lots of Minuteman missiles buried. I don't know if they've reduced the number or not, but you can drive all over western Nebraska and see them everywhere. There was one 6 miles from where I grew up and lived for years and years. So
Yeah, there's a major missile base field up there in Wyoming.
Can they accidentally go off?
Oh, that's a whole question. There's books on, the safeguards are considerable. However, you can buy some books on nuclear weapon close calls. There have been a couple. Yeah, closer than we would have liked close calls.
It's just amazing to me, we haven't had an accident that set one off, or somebody hasn't sold one to a bad actor that's set them off somewhere. It's a dangerous one.
Well, we're out of time. I wish we could stay another hour, but thank you, Ron. I understand more now what it's all about. Thank you, Zoomers, for joining us too. We hope to see you next week. Bye-bye.
Okay.
You still didn't hear about lithium batteries.
Righty.
We're in somebody's garage.